Hello everyone, and welcome to our project, the electromagnetic train. The materials and parts used. So for our supplies, we use a 5/8" wooden dowel, an 18-gauge copper wire, bare, a AA battery, and 15x2 mm neodymium magnets. And for our equipment, we use an electric screwdriver, 2 clamps, and 2 blocks of wood. And with our equipment and our dowel, we were able to make a coil that was around 19 inches long and had our battery run around 2.41 seconds for the track time. And that's around 8 inches per second or half a mile per hour. As we can see to the video on the right, the electric screwdriver is helping us spin the wooden dowel. And that spinning wooden dowel is helping us make our coil with the copper wire. Now, to use this, we're using 2 different people. One person to hold the copper wire in place, and one person to hold the electric screwdriver in place. Procedures. Number 1. Gather all supplies and equipment. Number 2. Wrap the coil around a tube slightly larger in diameter than a AA battery. For this project, we made this part easier by creating a system to wrap the coil quickly and tightly. Number 3. Connect the battery to 5 magnets on each side so that the magnets are opposite in polarity. Number 4. Place the AA magnet system with the negative side going in first and release it. Blueprint. Originally, we anticipated a big track that held obstacles, but unfortunately, with the given time, we were unable to do so. On the right, you can see a diagram with the potential model, the realistic model, and our final model. The reason why we chose copper. On the right, we see an aluminum wire and a copper wire. The copper wire was the obvious choice. Without electricity, it is not magnetic, meaning our neodymium magnets will not instantly stick to the wire. And it's one of the most efficient conductors of electricity, and so our battery can easily create a current in the wire. One of the other materials we considered was the aluminum wire, and a coil could have been provided to us by our physics department. However, it did not fit the project because of the super attraction it had with our magnets. The neodymium magnets kept instantly sticking to the aluminum, therefore making it unviable. How the train works. The Hyperloop consists of a AA battery with 5 neodymium magnets attached to both ends. The battery magnet acts like a train, which is passed through a copper coil, which is our track. The train is propelled due to its electromagnetic force, in particular Ampere's law and Faraday's law. The copper coil conducts electricity well, and when the battery magnet is introduced, there is a change in voltage in the wire due to Faraday's law. The change in voltage leads to a change in current, which then leads to a change in the magnetic field, which then can push the battery magnet forward. As you can see on the video to our right, the battery moves at a constant velocity throughout the wire. The reason this is so is because the battery has a constant change throughout the wire. And so the magnetic field that's created at each separate point along the wire is the same strength, no matter where the battery is moving inside that wire. Some extra information. Number 1, do not leave the battery within the coiled copper wire, or it'll heat up very, very, very quickly. So please do not leave the battery within the middle of the track. And number 2, in our project, we connected our coils by soldering them together. So if you have like 2 smaller coils, you can connect them pretty easily and make a longer and longer and longer and longer track. Faraday's law. A change in the magnetic environment of a coil of wire will cause a voltage to be induced in the coil. And when a magnet is moved inside of the coiled wire, there's a change in the magnetic field and the magnetic flux through the coil. Lenz's law states that an induced electric current flows in the direction that produces the magnetic field such that the current opposes the change in the magnetic flux that induced it. and so the copper wire becomes magnetic. And important to note, the magnet must keep a velocity or the induced magnetic field in the wire will cease to be generated. It needs to keep moving. Ampere's law and its applications. The magnetic field in space around an electric current is proportional to the electric current which serves as its source. This is very similar to how the electric field in space is proportional to the charge which serves as its source. The copper wire in our project is a solenoid, which is defined as a long straight of coil of wire which can be used to generate a nearly uniform magnetic field. As you can see to the image to the right, all the magnetic field lines are pointing in the same direction, and most of the density of those field lines are inside the coil. Because of all these field lines inside the coil, it helps propel our battery forward. The Lorentz force law. The Lorentz force law is a combination of electric and magnetic force on a point charge due to electromagnetic fields. There has to be moving charge in a magnetic field, otherwise there is no Lorentz force. And the direction of Lorentz force can be determined by the right-hand rule. Now for the case of our battery magnet, this force helps propel the battery forward when it's moving. Modern-day magnetic trains. As of today, there are 6 commercial electromagnetic trains located in Japan, South Korea, and China. The concept of the train is very similar to that of our project, but at a much bigger and more complex scale, and is used for transportation. Because of these magnetic fields, the train is pulled forward from the front and pushed from the back, just like how our battery magnet is. And even at incredible speeds, the levitating train's design ensures a smooth ride. And as you can see on the right, that's Japan's LO Series SC maglev train. It can get up to 375 miles per hour, takes around $74.7 billion to be built, and is expected to open in 2037. And in summary, we applied Lenz's law, Faraday's law, Ampere's law, and the Lorentz force law. And we built an electromagnetic train. Thank you for listening to our presentation.